Okay, so this video we're briefly going to discuss the Pythagorean theorem, work a few examples, and then we're going to relate it to two-dimensional distance immediately following. So we're all pretty familiar with the Pythagorean theorem. It simply says a squared plus b squared equals c squared, right? And that's easy to remember, but without context, it's not going to make any gosh dang sense. Okay, so what we really mean to say is leg 1 squared plus the other leg, we'll call leg 2 squared, should be equal to the hypotenuse squared, or uh, L1 squared plus L2 squared equals h squared. Okay? And let's talk about what legs on a right triangle even are. So a right triangle is called so because it has, that's right, you guessed it, a right angle. Okay, and the two sides of the triangle that form the right angle, this one and this one, the two that are perpendicular to each other, they are in fact the legs, right? So the legs actually form the right angle. Okay, and then you have what's called the hypotenuse, the longest side of the right triangle. But that can get kind of deceiving depending on the kind of picture you're looking at. Um, the hypotenuse, yes, it is the longest side, but it's important to remember that the hypotenuse is always opposite. It's always opposite of the right angle. Okay, so now that we've got that down, right, we've got an actual example here that we can refer to, and this is the same example that's on your do now for this lesson. So let's look at that. Here we see point A and point B are an unknown distance apart, right? And we've already discussed quite a bit about distance in one dimension, right? But here we see, well, we've got two dimensions, namely x and y, right? So it's not going to be so simple as just taking the 2 points, subtracting them, and taking the absolute value, right? But we can apply that same logic. So point A from here to here, forming this dy, the distance in dimension y, well, that distance is simply 4, right? And same idea here with dx, or our distance in dimension x. We see that we have a distance of 3, right? So, I mean, if we look at this the right way, this is a really simple problem. This is the length of dx here, or sorry, dy. This is the length of dx here, right? And we're looking for the missing hypotenuse, right? Well, leg squared plus leg squared equals hypotenuse squared, and we'll call this d2 for distance in 2 dimensions. So leg squared plus other leg squared equals our missing hypotenuse squared. So we end up with 16 plus 9 equals our distance squared. And we don't want to know our distance squared. Well, duh, we just want to know our actual distance, right? So 16 plus 9, that gives us 25. And we need to get rid of that right there. That is an exponent, right, in case you forgot. And the way we're going to get rid of that exponent is by doing its inverse, just like we always do in algebra. The inverse of squaring something is to take the square root of it. So if I take the square root of both sides of the equation, because what I do to one side I have to do to the other, if I take the square root of both sides, I get that the distance between point A and point B is 5. Okay, so here's an extra credit opportunity for you. I'll go ahead and pause a second here, take a picture of this, or do whatever it is you need to do. But be sure and take advantage of this extra credit opportunity. Anyway, so we can use the Pythagorean theorem to calculate the distance between 2 points in 2 dimensions, right? And that's exactly what we're going to do here with these first few examples. So starting with triangle 1, we're looking for our distance in 2 dimensions between point A and point B, right? And we can easily do that just using the Pythagorean theorem. We're basically looking for the missing hypotenuse, right, on a right triangle. So here we go again. Leg squared plus the other leg squared will be equal to our missing distance squared, or our hypotenuse squared, right? So 81 plus 144 equals our distance squared. That is going to give me 225 when I add those two together. Take the square root on both sides because we want to know the distance, right? Not the distance squared. And we get that our distance is equal to 15 here. Okay, let's look at another one. And I'll use yellow. Okay, so here we are looking for another missing hypotenuse, shall we say, right? So we're looking for this missing distance here. That is equal to leg squared plus the other leg squared. So 5 squared plus 12 squared is going to be equal to our missing distance squared. So that's 25 plus 144, right? That combined together gives us 169. Take the square root of both sides, and our missing distance is simply 13. One more example on this page. And I'll use pink, why not? Okay, so this is where it can get confusing. Well, where's the hypotenuse? That's why we need to understand the hypotenuse is always opposite of the right angle of the 90. Okay? So that means leg squared plus other leg squared will be equal to our missing hypotenuse squared. Okay, so 15 squared is 225 plus 36 squared, which is 1,296. Okay, so that plus 225, that gives me 1,521, whose square root is simply 39. So this missing distance here would be 39. Okay, so now we've got a little bit uglier examples. So now we're trying to find missing legs on right triangles, not anymore with the missing hypotenuse. So let's jump right into that. So we can still use the Pythagorean theorem to find a missing leg, right? We don't only have to use it if we're just trying to find a missing hypotenuse, right? So we can still say leg squared plus leg squared. Except I have to say b squared, right? I can't say I don't know what b is, right? So leg squared plus leg squared equals my hypotenuse squared, right? So 5 squared is 25 plus the missing leg squared equals 13 squared, which is 169. Okay. Now this is a simple equation that we can solve. So I get rid of this positive 25 by just doing minus 25 to both sides. B squared equals 144. I don't want to know b squared. I just want to know b, right? So I'm going to take the square root of both sides like I would, any other time. And the missing leg b is simply 12. Okay. Let's do another one. Okay, so right here, leg squared plus leg squared equals hypotenuse squared. We're looking for the missing x. Okay, and again, I'm putting them where they go in the formula. So leg 1 squared plus leg 2 squared equals your hypotenuse squared. Okay, so x squared plus 225 equals 400. X squared is going to be equal to, brain fart, 175. I thought that was right, but I didn't think I would use such an ugly number here. Okay, and we get sorry, got distracted. And we get that the missing leg x is going to be 13.23 thereabouts, right? Okay, so that's not actually what the calculator would tell you. It actually told me 13.22856, blah, 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 blah. In my class, we'll always round to the nearest hundredth, right? And notice I use squiggly lines instead of an equal sign like I did here. Okay, so these squiggly lines are just a cute way of saying approximately, right? So x is approximately 13.23, right? It's exactly equal to, right? We could say that it's exactly equal to the square root of 175. And the square root of 175 is therefore approximately equal to 13.23. Okay, one more example on this page. So we're looking for another missing leg, right? That's not the hypotenuse. The hypotenuse is right over here, opposite of our right angle. Okay, so d squared plus 10 squared is equal to 20 squared. D squared plus 100 equals 400. And subtract 100 from both sides, and we get that d squared is equal to 300. D is therefore equal to the square root of 300, which is approximately, that one I don't know off the top of my head, 17.32. It's about 17.32. Okay, so this missing leg would be about 17.32 in length. Okay, so now let's get into how we can apply this to two-dimensional distance, right? So we've got 2 points, A and B here, right? So A is at -5, right, by +3. Okay, so that's my x1 and y1. Okay, and then point B is at +5, right, and +10. And if we just kind of connect the dots here, try to draw something that's somewhat of a straight line, okay, you'll start to notice a very familiar shape is taking form, right? So we see that we have, holy dog crap, a right triangle. Okay, so because we have that, okay, what we can simply do, I'll just put another dot right there. What we can simply do is say, we have a distance in x, right? So this is x1 minus x2's absolute value in length from here to here, right? So from this point to this point. Okay, and we can also say that from this point to this point, right? Well, this would be our distance in the y dimension, right? That's how long this side right here would be. Okay, so we've got a distance in x, we've got a distance in y, right? What we can do is come up with a formula for this. I'll go back to using green. So if I take my x distance, that's the length of that leg there, right? So I can say x1 minus x2 all squared, absolute value, right? So this is like leg 1 squared. Plus, well, we know we need leg 2 squared, right? Well, this would be our second leg, our distance here in y, right? So plus our distance in y is equal to, and here in orange, I can call this our two-dimensional distance from point A to point B. Or it's like our hypotenuse, right? So I can say leg squared plus leg squared equals hypotenuse squared. Okay? And I don't want to say our distance squared, obviously. I just want to say our distance. So I'm going to take the square root of both sides, and that gives me our two-dimensional distance formula, right? So our two-dimensional distance formula is simply this. Distance in two dimensions, distance in two dimensions is simply equal to the square root of your x distance all squared plus your y distance all squared. Okay, so let's practice using it a few times. So here in this first example, we're trying to find the distance between A and B. Okay, so A is at negative 3 by 4. We'll call this x1, y1. B is at 3 by negative 4. And we'll call that x2, y2. Okay, so to find the distance between this, well, we've got a super cute formula that we can use. We don't need to sit here and try to draw a crazy picture like we did here last time. We can easily just use, well, I guess I could have just left it there, this formula right here. So let's go ahead and do that. So my x distance would be negative 3 minus 3's absolute value. And of course, we're going to want to square that in accordance with our formula, plus our y distance, so 4 minus negative 4, all of that squared. And then we know, well, we're going to take the square root of that, and that's going to give us our distance in two dimensions from point A to point B. Okay, so quick maths. So negative 3 minus 3, well, that gives me negative 6. The absolute value of negative 6 is just 6, and then 6 squared, well, that just gives me 36. Plus, same idea here, 4 minus negative 4, well, that just becomes a positive, right, because we've got a double negative there. Okay, so that becomes 4 plus 4, which is 8, right? And the absolute value of 8, again, would just be 8, and then 8 squared. Well, that's just going to be 64. So now we've got the square root of 36 plus 64, or when we combine those, the square root of 100, right? And of course, the square root of 100 is simply 10. So our distance in two dimensions from point A to point B here would be equal to 10 units. Okay, let's apply that again a couple more times. Erase all this and give myself some room. Okay, so now we don't have a cute picture to draw from. We're just being asked, what's the distance between points A and B, right? We still always want to label. So point A is x1, y1, point B is x2, y2. And that's all the information that we need. So our distance in two dimensions would be equal to the square root of absolute value of our distance in x, so x1 minus x2's absolute value all squared, plus our distance in y, so 14 minus 6's absolute value. And of course, we're going to square that also. Okay, so 11 minus 17, well, that's just negative 6, plus 14 minus 6 is 8, right? And of course, now we can just say, well, that's just 6. That's just 8. So now we've got, so 6 squared is 36, plus 8 squared, which is 64. These numbers look familiar, don't they? Which is equal to the square root of 100. And of course, we know our distance in 2 dimensions is going to be equal to 10 again. Okay, so that was a cool coincidence, I guess. Okay, let's look at example 3 now. So again, we're going to label x1, y1, x2, y2. Our distance in 2D is going to be equal to square root of our x distance squared plus our y distance extend that out over a little bit more. Okay. And negative 15 minus 105, well, that's going to be negative 120, whose absolute value, of course, is 120. Okay, negative 12 minus 38, well, that's going to be negative 50. And whose absolute value is simply 50. 120 squared, we'll just think of 12 squared. Well, 12 squared is 100, and 12 squared is 144, so we would just add 2 zeros to that. So we have 144, with 2 zeros. And then 50 squared, well, we're just going to think of 5 squared, that's 25, and again, we're going to add 2 zeros to that as well. So plus 2,500, like so. So now we've got 14400 plus 2,500, right? And you can relate this back to if the zeros were just gone. Well, we know that's going to be 16900, whose square root would simply be 130. So that means our distance in 2D for that problem would be equal to 130. Okay, so for the sake of brevity, I'm going to go ahead and cut off the video here. I think we've worked plenty of examples. Like I always tell you, if you need anything, come and see me and or shoot me an email. Otherwise, goodbye.